Okay, we're coming to the end of integration. I mean, you've sort of got two more integration techniques. And then we've got numerical approximations, and then we've got some application stuff. But I'm afraid that one of the integration techniques we still have to cover is an extremely sort of technical integration technique. It's like the most technical technique we learn in calculus 2, and it's called trigonometric substitution. And trigonometric substitution is also, I would say, the most specialized integration technique we learn in calculus 2. It's designed to help us integrate some very specific square roots, and it doesn't have a lot of utility outside of that necessarily. Before I say what trigonometric substitution is, let me try to motivate this a little, because if I just come in here and put the substitutions on the board, it's going to look like I'm performing a magic trick, like I'm just pulling stuff out of a hat. So let's put an integral on the board that we actually already know how to take. 1 over the square root of 9 minus x squared dx. I mean, I say we know how to take this, depending on how well you committed the inverse trig stuff to memory. We can integrate this using the inverse trig functions. And when I was talking about the inverse trig functions and talking about integrals that look like this, I promise that even though that integral might look very artificial, I mean, we've got this square root. Where would this show up in the real world? And I said, well, it shows up in the real world, or at least integrals like that can show up in the real world when you have a right triangle. And in this particular case, a right triangle with a fixed hypotenuse. In a situation like that, I mean, say that this fixed hypotenuse is a ladder leaning against the wall, and it's sliding down the wall, and we are interested in that vertical distance x. Then this horizontal distance is this square root, 9 minus x squared. So we can see how integrals like that might show up in a applied situation. Trigonometric substitution is designed to help you compute integrals that come from the Pythagorean theorem. So it's designed, for example, to help you take integrals that look like this. Now, we don't need any special technique to take this integral. We can take this using just the inverse trig functions. But let's use this to illustrate how trigonometric substitution works. So the basic thought is if we have this right triangle, has three sides. And the side of the triangle that is appearing in this integral is by far the worst side of the triangle. Like x is simple, 3 is simple. The square root of 9 minus x squared is complicated. So the motivation for trigonometric substitution is the question, can we replace this complicated looking side of the right triangle with the simpler sides of the right triangle? And we ask, well, how could we do that? Well, if we want this side of a right triangle and the hypotenuse of the right triangle, we do have a field of mathematics that relates the sides of right triangles. That's trigonometry. So what we're going to do is we're going to give that angle a name. And we're going to write down the right triangle identity that the side of an angle is the opposite over the hypotenuse. Okay. Pause, take stock. This is the integral we're working with, and our variable is x. So we defined sine of theta to try to somehow replace this complicated looking square root with simpler terms. Now, if the sine of theta is x over 3, then x equals 3 times the sine of theta. And we can take this x and we can plug it in there. And when we do this, it's going to look like we've made things worse. This trigonometric substitution always looks really ugly when we perform it. But let's see what happens if we take this x and we plug it in here. 1 over the square root of 9 minus 3 times the sine of theta squared. And let me separate these. But now we have a problem. I mean, it seems like maybe we have several problems. We've replaced the integral and made it look worse. That's a problem, but a more fundamental problem is that our variable was no longer met. We've got theta as our variable, but we've got to dx here, and those are supposed to match. This dx is saying that our variable was x. Now, the step we perform here is similar to what we did when we had integration by parts, or similar-ish. If x is 3 times the sine of theta, then we'll say that dx is the derivative of this. D theta. So then we take that dx, we plug it in here, and we wind up, as I say, we wind up with something that does not look like an improvement on what we started with. This thing under the square root becomes way uglier, and then that dx gets replaced but somehow I am going to claim, if we take this terrible looking integral and we mess around with it algebraically in the right way, this integral will simplify significantly and we'll be able to take it. And when you're using trigonometric substitution, just like in the last section, when you use trigonometric substitution, you're going to be using the Pythagorean identity. The fact that the sine squared plus the cosine squared equals 1. And we're going to use this always to get rid of the square root. Let me simplify this thing under the square root. 9 minus 9 times the sine squared of theta. And then outside of the square root, we've got this cosine still hanging around. And what we're going to do inside the square root, again, we're interested in using the Pythagorean identity here. The cosine squared is 1 minus the sine squared. And this is in fact just how we used the Pythagorean identity in the previous section. me put a line to separate those. We pull out the 9. And we get 1 minus the sine squared. And then I said that this was a very technical method, lots of steps. The square root of a product is the product of the square root. So we are going to have the square root of 9. And we're going to have the square root of that. And the square root of 9 is 3. Yeah. So we get 3 times the square root of 1 minus the sine squared and we've got all of that. Good Lord, but there's nothing I can do to make this problem be nicer than it is. This is just how trigonometric substitution works. Some stuff cancels, or at least this 3 and that 3 cancel. And 1 minus the sine squared of theta is the cosine squared of theta. Again, that's using the Pythagorean identity. The integral of 1 divided by the square root, the cosine squared of theta, times the cosine of theta. For a while, it must have seemed like I was lying to you when I said that stuff was going to simplify, but the square root of the cosine square is the cosine. The square root goes away. Our cosines cancel. We're left with 1. The integral of 1 is theta. But what the heck is theta? Well, similar to when we performed U substitution, we'd wind up with U's and then we'd have to convert back to X's. Here we have a theta. What was theta again? Well, the sine of theta was X divided by 3. Notice that we don't have a formula for theta on the board. Nowhere on the board do we have what theta is equal to. But if the sine of theta is x divided by 3, then if we take the arc sine of both sides of this equality, the arc sine and the sine cancel, and we have that theta is the arc sine of x divided by 3. And the integral then is the arc sine of x divided by 3, thus a constant of integration. This particular integral, as I say, we could have gotten that using just the inverse trig stuff. But that's an outline of the technique. And there's no sugar coating this. At least trigonometric substitution was certainly my least favorite of these techniques when I was an undergraduate, and I still don't love it as a professor. But it's part of the standard curriculum. It's not something that I'm allowed to remove from the curriculum, assuming that we want students to be able to transfer credits to other institutions. So we just have to kind of put up with this. And let me summarize. There are multiple substitutions. We've seen one of them. If you see the square root of some positive number minus x squared, consider the substitution x equals a times the sine of theta dx equals a times the cosine theta d theta. And the picture you should have in your head here is we've got a right triangle and we've got x and a. And that square root is the other side of the triangle. I guess we should attempt another example. I say attempt just because the first example took almost exactly half of the class, so who knows whether we'll finish this out. But let's take the example we were just looking at. And let's modify it a little. So let's replace that numerator with x cubed. So this is no longer going to just be an inverse trig function. At this point, we legitimately need some kind of special technique. Again, there are no absolute rules in calc to this. If instead of x cubed, we had x, then even though we have this square root, trigonometric substitution would be overkill. If we just had x, we could hit this thing with U substitution and have a much easier and quicker time. But we have what we have, and what we have is x cubed. So let's try this substitution. So 9 is 3 squared. So the recommended substitution that we might try here is x equals 3 times the sine of theta, then dx equals 3 times the cosine of theta d theta. And I guess the nicest thing I can say about this substitution is that there are lots of just kind of plug and play elements here. Everywhere x appears, we're going to replace it with this recommended substitution. And then when dx appears, we're going to replace it with that recommended substitution. And we get 3 times the sine of theta cubed divided by the square root of 9 minus 9 times the sine squared of theta. And then we've got 3 times the cosine of theta d theta. And then I've said this before, I said it in Math 151, that I think a lot of times it's the algebra that's as much of a pain as anything else. Let's see what we can do. A product cubed is going to cube both pieces of the product. So 3 cubed is 27. And then we're going to have the sine cubed. These square roots are always going to be dealt with in the same way. The number out front is going to be pulled out. And our goal here is always going to be to use the Pythagorean identity to get rid of the square root. And we've got this 3 times the cosine of theta hanging around. So the square root of a product, again, that's going to be the product of the square root. So let me copy this. The top I'll just leave unchanged. The bottom, as I say, the square root of a product will give us the square root of 9, which is 3, times the square root of 1 minus the sine squared. And then we've got 3 times the cosine of theta d theta. Well, halfway mark, probably. Those constants, you could pull them out, you could do some cancellation. This 3 up here, and that 3 down there. Cancel if you want to do that. And now the real point of all of this is to get rid of the square root. It's to use the Pythagorean identity. To turn the thing under the square root into a square. Again, we're using, where are we? Could have just written it again, but we're using the Pythagorean identity here to go from, in this case, to go from sines to cosines. So this 1 minus the sine squared turned into a cosine squared. And good news, bad news, I guess. The good news is that we have some cancellation. We get rid of the square root, just like we wanted. And that leaves us with a cosine up top and a cosine down below. The bad news is, I mean, this integral we have still requires some work on our part. So we are not done, alas. But pause for a second and take stock. Odd powers of the sign were what we were doing last section. So we should be able to deal with this sine cube. This 27 and can just go out front and get out of our way. So the trick for dealing with odd powers was to pull one of the odd powers out. So that we're left with an even power. And then use the Pythagorean identity to deal with the even power. Sine squared is 1 minus the cosine squared. Good heavens. Well, this then requires a U substitution. Okay, at least we're sort of approaching the end here. If we let U be the cosine, du is, nope, du is the negative sign. So we need a negative. We can put that negative in. And what I'm going to do in the next frame, I'm going to take this negative sign and I'm going to pull it out. So negative 27. And then I'm going to turn to U. 1 minus U squared, U. And now U minus 1/3 U cubed. We've got our constant of integration. And we are approaching our final answer here, I promise. U is the cosine of theta. So 27 times the cosine of theta minus 1/3 the cosine cubed of theta plus c. And as I say, port is in sight here. If we can go from thetas to x's, we'll have taken this integral. ports in sight, so let's not go on to the rocks at the very last minute. Remember, we have that 27, that negative 27. So what's the cosine of theta? Well, what was theta in the first place? We know what the sine of theta is. The sine of theta is x divided by 3. What we don't see is anything involving the cosine. So this is why I said that we should have a picture like that in our mind. Because if we have a picture like this, the cosine of theta is the adjacent side over the hypotenuse. If we have this picture, we can use right triangle trigonometry. And in this particular case, we've got 9 minus x squared. A is 3. The cosine of theta is the adjacent side over the hypotenuse. So not the nice looking expression. There's the adjacent side. There's the hypotenuse. So negative 27 times the cosine of theta. So negative 27 times this. Plus 1/3 times this cubed. My whiteboard pen thing vanished at the very last moment. Let's see, let's try stopping the share and then sharing it again. There. So, thus, 1/3 times this cosine cubed. And then we've just got our constant of integration. And this we could simplify this a little. We could make it look slightly less awful. I mean, 27 divided by 3 is just 9. So this could become negative 9 times that square root. And then, well, there's not a lot we can do to this to make it look great. Maybe that will just leave be. But I mean, nothing you can do to this is going to make it look like a nice expression, because it isn't a nice expression at the end of the day. And that's the idea behind trigonometric substitution. There are 3 substitutions, and by 3 substitutions, you see this piece of advice here, that if you see a square root of a specific form, you might try letting x be some trig expression. This is what I mean by a substitution. So there are 2 others we have to see. I don't want to spend too much time on trig substitutions. I mean, they're very intricate, as you can see, but maybe we'll end up spending tomorrow finishing this material off, maybe and Wednesday, not 100% sure, but we'll certainly start the next section this week. All right, it's not my policy to, if I can help it, to do a lot of grading over the weekend. So I did not get to your tests, but I'll get those graded promptly now that it's the work week. And I mean, I need to figure out how to weigh your grade book so that tests and your quizzes and stuff are all weighed appropriately. But I'll see you tomorrow, and I'll get everything graded, and we'll continue with this. So look forward to that.